Greetings. In this video, I'm going to go over some of the highlights of Chapter 3 in your textbook on functions and graphs. This video should not take the place of you going through the various study plan offered in my math lab and or working problems in your book, odd problems, and checking them in the back of the textbook. Those are both ways to learn these concepts. It also isn't a replacement for reading, for studying the textbook. Taking notes as you read it is the best way probably to learn. Well, the best way to learn is doing the problems as you read, but taking notes may also be really beneficial. Section 3.1 is all about functions, and hopefully functions aren't something new to you. Here we have a graph of a function. So this is a graph of poverty rate in the United States, where we are comparing seeing how the rate has gone up and down over the years. The areas on this graph that are in blue are times of recession in the United States between 1959 and 2011. What makes this graph a function is a question you should ask yourself if you don't automatically know the answer. We'll come back to that. So here's the definition from your textbook. A function consists of a set of inputs. That set of inputs is called the domain. A set of outputs, the set of outputs is called the range. And there is a rule that determines that for each input, there is only one output. In a function, each input produces a single output, but different inputs could produce the same output. We sometimes think of functions as we describe them as function machines. This is what I did when I taught elementary school and middle school, and we talked about functions in those classes. And we talked about really simple functions in those classes. We would draw a box on the chalkboard. That was when we had chalkboards even rather than dry erase boards, because it was back in the day, yo. And so we would have a number go into the function machine, and some other number would come out. And so a 3 might go in, and maybe my function machine adds 4 to it. So a 7 comes out. And so in, say, middle school, we start talking about negative numbers. Maybe a negative 10 comes in, and then a 6 comes out. Maybe a 0 comes in, and then a 4 comes out. But notice for every number that goes into the function machine, only one number comes out. You'd never put in a 3 and get a 7 or a 9. Now, it's possible that you could get the same answer from different inputs. You couldn't with this one because you're just adding 4, but you could for others, right? There's more than one way we could reach a certain number. But whatever the input is will only give a single output. So there might be more than one way in a function to get to 7 or 10 or 22. But whatever number comes in will only give us a single output. And that's why that graph that we saw is a function. Because every value on our x-axis here, let me actually get the laser pointer here so you can see a little better. Every value on the x-axis has just one value on our graph. So 1980's value looks to be about 14, give or take. So a poverty rate of about 14%. Now, there are other times when we have that poverty rate. We have it again maybe in 1987. We have it again 96, 97. We have it again maybe 2007, something like that. So we can get that different times, but in 1980, there is just one poverty rate. In 1965, there is just one poverty rate. In 2000, there is just a single poverty rate. There is one output for every input has just one output. So unless otherwise stated, we're going to assume that the domain of any function is the largest possible set of inputs that each produce a real number as the output. We are not going to worry about imaginary numbers in this course. Some of the chapters that we don't cover, could deal with imaginaries. So they talk about quadratic functions, which could have imaginaries, but that is not an issue in linear functions, which is the point of finite as we teach it here. So each of these equations defines y as a function of x. We want to find the domain of each function. Remember, the domain is our inputs. And so our domain here is everything that x could be. And what could x be? Well, x could be any number. You could have negative 12, you could have 0, you could have pi, you could have 33 million. The domain here is the set of all real numbers. We sometimes write this in what's called interval notation. And so we write this as parentheses, negative infinity, comma, infinity, parentheses. Sometimes we also write it in shortcut form with this symbol for the reals. Sort of a fancy R, an R with an extra bar on it. So you might also see that. Here we have the square root of x minus 6. Could any number be x? No, because we're talking about real numbers only in this course. And so if we had a number that's bigger than 6, we'd have a negative square root, which is imaginary. So for this to be real, for y to be real, x minus 6 has to be non-negative. And so we solve that inequality, and we see that x must be greater than or equal to 6. So in interval notation, that is written as bracket 6, comma, infinity, parentheses. Remember, the bracket indicates that the number after the bracket or in front of the bracket, if it's at the end, is part of the solution set. So 6 is a valid answer. Infinity is not part of the solution set. Infinity will never be, because infinity is not a number. It's just an idea. It's just a label. Here we have y equals 1 divided by x plus 3. Again, ask yourself here, could x be any number? And our answer is no. Why not? Because we can't divide by 0. What would make our denominator 0? It would make it 0 if x were negative 3. So the domain consists of the numbers in the intervals negative infinity to negative 3 or negative 3 to infinity. And sometimes in set theory notation, we write that with our union symbol, which means or. So you might also see it written that way. So here's what your screen on the calculator might look like as we're inputting x and y variables for some function. And the thing that we'll see is that you're going to have just single x variables. You wouldn't ever repeat 5 or 6 or 7. They don't have to be integers. You could have 5.1, 5.2, 5.3, 5.4, and 5.5 as inputs. You might have 5, 10, 15, 20, and 25 as inputs. You might have negative 12, negative 11, negative 10 as inputs. But you would never see 12, 12, 12, 12, 12 as inputs. It wouldn't be a function if you did. And this output screen specifically is from example number 11 on page 121 of your textbook. And it asks you to use the table feature of a graphing calculator to find the projected sales of the company in the previous example for the next 10 years. So here we would see years 5, 6, 7, 8, 9, 10, as well as 11, which is outside what we're being asked to find. So to do this on a graphing calculator, we would first click y equals, and then we would put the function given in the problem to us. And so I'm going to put that in now that the textbook gives us. So you see I've entered that function into the calculator. Then on the TI, I'm going to go to the second key and hit table set. And I want my table start to be number 5 because we're interested in year 5. And then I'll go to the second key and I'll hit graph, which gives me to the table. And I see something that looks very similar to what you see in your textbook. It's not identically the same because this is a different type of calculator, but it's roughly the same. It just has some more columns in it. Same answers you see in the textbook and on our PowerPoint screen. Hard to see the calculator compared to now, but we have 184.5, 184.5. And this is in thousands. So it'll be $184,500. So we can use our calculator if we have a graphing calculator to do some of these tables. So that's a rough overview of section 3.1 in your textbook. We will next take a look at section 3.2. Section 3.2 is all about graphs and functions. So it's really about representing functions in visual form. We see here a graph. This is a graph of a linear function. A linear function is always graphed as a straight line. If you took a course like Math for Liberal Arts, or if you remember algebra from high school, you might remember that a linear equation will always be graphed as a straight line. Equations are examples of functions. Now, not every equation is a function, but all functions are special equations, basically. Except instead of saying y equals 0.5x minus 3, here we use function notation and say g of x equals 0.5x minus 3. Just like with an equation, this tells us some things. It tells us that our y-intercept is negative 3. And it tells us that our slope is 0.5, or 1/2. In other words, for every one value it goes up, it goes over 2. 1 up over 2, 1 up over 2, and so on. Remember, rise over run. You might remember that from high school. Linear functions are the predominant function we're going to work with in this course. Sometimes finite math courses deal with quadratic functions and rational functions and polynomial functions. This course is primarily focused with linear functions. And that's because this course doesn't have college algebra as a prerequisite. Here is an example of what's called a piecewise function. And a piecewise function is two functions. I shouldn't say it's two functions. It's one function that has two different conditions. So if x is less than or equal to 2 here, our function is we add 1 to x. So when x is 2, y is 3. When x is 1, y is 2. When x is 0, y is 1. When x is negative 1, y is 0. And that keeps going on to negative infinity. As soon as x gets bigger than 2, what we do then is we multiply x by negative 2 and we add 7. So here we have x equals 3. And so that means we have negative 2 times 3, that's negative 6, plus 7, so that's y is 1. So again, this is a piecewise function. This happens to be a linear piecewise function because we have straight lines. Piecewise functions are always going to be introduced with a single brace like this, or almost always. And it will give us our conditions. We could also have linear functions that have jumps or gaps in them, like this one does. So here we again have two parts to the function. If x is less than or equal to 3, we take x and we subtract 2. That is this part. Notice it includes or equal to 3, so we have a closed circle or a filled circle here when x is 3. When x is greater than 3, we multiply x by negative 1 and we add 8 to it, and that's what this other part of the graph shows. Notice here we have an open circle because 3 is not part of the function here. 3 is down here, it's not up here. And then another type of function that is linear that we aren't going to do a lot in the course, but shows up in your homework and your quizzes and stuff, potentially, is the absolute value function. Remember, absolute value, we're interested just in how far something is from 0 on the number line. It doesn't matter what direction. And so we say absolute value is always positive. So if I wanted to find the absolute value of -7, my answer is going to be 7. If I wanted to find the absolute value of +7, my answer would also be 7. So for absolute value, our answer, whatever's in the absolute value sign, will always be positive when it comes out of those signs. So here we have a very simple rule. We're finding the absolute value of x. So in other words, if x is 0, all right, so when x is 0, y is also going to be 0 because the absolute value of 0 is 0. In other words, it's at the origin. So we'd plot that point right there. If x is 1, y will be 1. So when x is 1, y is 1. If x is -1, y is still 1. If x is -2, y is going to be 2. If x is +2, y will still be 2. And so what we get with absolute value functions are two straight lines. They're always going to look like some sort of V. Now, sometimes they might be an upside down V. They might be a sideways, they might be rotated somehow, but it's going to have some sort of straight V shape. It's going to be two straight lines connected in one spot that are symmetrical. We could fold them over themselves. All right. So for our specific example here, we have this piecewise function. And absolute value functions can be defined as these piecewise functions. So f of x equals x if x is greater than or equal to 0. And f of x equals -x if x is less than 0. So the right half of the graph, where x is greater than or equal to 0, will consist of a portion of the line y equals x. And the left half of the graph, where x is less than 0, will consist of the portion of the line y equals -x, which we could graph by plotting any 2 points on that line. So here we have a step function. This one happens to be the greatest integer function. And so what the greatest integer function is doing here is it's saying that this value of x, notice it's in brackets. This is one of the times we use brackets specifically in math. The other times when we work with matrices. And so what the brackets tell us is saying that this represents the largest integer that is less than or equal to x. So the largest integer that is less than or equal to 1, or the largest integer that is less than or equal to 2, or the largest integer that is less than or equal to 3, and so on and so forth. So, in other words, pi would be right about here, we'll say. That's about 3.14. Pretend that it is anyway. And pi would be part of this range. So we would say that if we put pi in here, that would actually equal 3. Because 3 is the largest integer that is less than or equal to this value. If we put 6.2 in the brackets, our answer would be 6, because 6 is the largest integer that's less than or equal to that value. There are ways to get the greatest integer function on calculators. So it's found under the math function. And if we go to number or num and choose int, whoops, I have to do it from the main menu though, from the main screen. There we go. If we go to math and go to number and choose integer, and so if I put, let's approximate pi, it's going to tell me that it's 3. It's always going to go back and tell me what it is. So that's a nice handy way of doing it. And this is a command on many different calculators that are graphing calculators. This is the graph that I was mentioning. This comes from example 6. This has to do with the cost of mailing letters. So up to a certain number of ounces or half ounces, depending where it's being mailed to, is a certain cost. The next thing we talk about in this section is graphing a function by plotting points. To do this, the first thing we want to do is determine the domain of the function, as we did in chapter 3, section 1. And then we want to choose several numbers in the domain of f. If possible, if they are in the domain, we always want to include some negative numbers and some positive numbers. And it's often usually good to include 0 also, because 0 is usually easy to work with. And then we plot the points. The more points we make, the more points we plot, the more accurate our graph is going to be. We would use those points, as well as any other information we might have about the function, to make an educated guess about the shape of the entire graph. Unless we know something to the contrary, we're going to assume that the graph is continuous. It is unbroken wherever it's defined. So unless we're told it's a piecewise graph or a greatest integer graph or something like that, we are going to assume that it is a continuous graph. A graph is continuous if we could follow it with our pen without lifting up our pen off the page. So this would be a continuous graph. An absolute value function is a continuous graph. This is not a function, but it's a continuous graph. On the other hand, if we have, let me plot the xy coordinates here. This is not a continuous graph. We have a gap here. But we will assume in this course graphs are continuous unless we have reason to believe otherwise, unless the problem indicates that they aren't. So here we have an example of a continuously plotted graph. This is the graph of the function is 3 minus the quantity x cubed divided by 4. This is at the top of page 128 in your textbook. And it shows the points that they chose to graph this. Here we have an example of a piecewise graph. This is on the same page in your textbook, page 128. And again, that's going to show you a table that is used to graph. This is a good example where we definitely need a negative values to make sense of this graph, as well as positive values. And because it's piecewise, we need positive values from throughout the function. And then figure 3.12 is about reading a graph. This is another problem from your textbook. And so this is looking at the median sales price of new homes in different regions of the country from about 2005 to 2011 in thousands of dollars. And so one skill, of course, is being able to read a graph and to be able to make comparisons in a graph. So one question we might ask is, how do prices in the West compare with those in the Midwest over this period? And we could see that at the start of the period, prices in the West were were a little more than $100,000 more on average than they were in the Midwest. And that prices in the West were hit much more hardly by the financial crisis of 2008 than prices in the Midwest were. They went down in both places over these sort of struggling years, but they didn't go down as much in the Midwest as they did in the West. And so by 2011, the difference in prices, instead of being a little over $100,000 on average, was probably only about $50,000, maybe, right around $50,000 on average. So you see that that difference in price has decreased over time. And we notice that with the exception of 2007, the Northeast had the highest prices. We also see at the start of this period, the South had the lowest prices, but then it looks like the South is gradually increasing average prices over the Midwest throughout much of this period. So just some ways that we can interpret that particular graph. And then this is a graph of a function whose rule is the average interest rate of a 30-year fixed rate mortgage. A fixed rate mortgage is one where the interest rate that you get when you take out the mortgage stays the same. It doesn't change, even if the market interest rate changes, unless you refinance your house or do something else to get it to change, which you might do if the interest rates drop. So on this graph, again, we could see that in 1985, the average interest rate for a 30-year mortgage was 12%. On the other hand, the low in this graph was in 2011, where that average mortgage rate had fallen to about 4.5%. We see that along the way, it had some dips and then it would go back up a little bit. So we noticed that it dipped in 1987, then it rose again a little, then it fell again in 1993, and then it rose a little bit, fell back in 97, rose a little bit, then down, rose a bit, and really the overall trend, both over the entire graph and certainly since this last peak in 2000, with the exception of maybe just 1 or 2 years, has been a downward trend up until 2011. And then the vertical line test. You might recall the vertical line test from previous math courses. We can tell if a graph is a graph of a function if it passes the vertical line test. This means that no vertical line intersects the graph at more than a single point. And you can do this by moving your pen or pencil across a graph or a piece of paper across your computer screen. And if that piece of paper or that pen or pencil held vertically doesn't cross the function graph at more than one point, then it's a function. Otherwise, it's still an equation, but it's not a function. We call that a relation. If we have a graph that's not a function, it's called a relation. So this would be an example of a function of a graph that is not a function. This is a relation, not a function. And we can tell that because it intersects the graph at more than one point. So this dashed line is our vertical line. We see it intersects it here at 3, -1 and here at 3, 2. That's not the only place, right? It intersects it at 2 points everywhere except at the very, at the very vertex of the graph here at about -1.5, 0.5 or so. So this is not a function. This is a relation. Here we have some examples. Now our first example here, this is a function. For this, we could do the vertical line test. I'll use my calculator here as an example. So as I move my calculator screen across this function, notice it doesn't intersect at more than a single point at any time. That makes this a function. But here, notice right here, it intersects it at this point and at this point. Immediately I know, not a graph of a function. Here, same, it also does not appear to intersect it at more than one point. This is a tricky one, and your textbook mentions that. This has to do with the resolution of a calculator. And so be cautious with this. You might think that at 1 it becomes a straight vertical line, and a vertical line would not pass the vertical line test, obviously, but it doesn't. If we zoomed in, we would see it does have a slope. The slope is not undefined. So that's an important thing to keep in mind. As I always like to say, you have to be smarter than the calculator. And I know you all are smarter than the calculator, but people tend to put too much faith in what the calculator does. The calculator is an incredibly useful tool, but you have to know how to use it effectively. And so what we see here is this would be the table of the values that we see in that calculator. And so we see that we don't have the same value for x ever. So this is fine. This is a function. And this final screen is a zoomed view of that calculator screen. So it's a good place for us to stop in chapter 3. We'll do a follow-up video where we'll talk about some applications of linear functions.